Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on January 14, 2026, just 2 days ago. It reveals that a focused 7 billion parameter model can beat massive general-purpose models like QN3VL and GPT-5.2 on dermatology tasks, achieving a 12% jump in top 1 accuracy. The paper is titled, SkinFlow, Efficient Information Transmission for Open Dermatological Diagnosis via Dynamic Visual Encoding and Staged RL. And as we will see later, the implications for building reliable medical AI without relying on massive compute are quite significant. Alright, Figure 1 maps out the SkinFlow framework, which splits training into 2 reinforcement learning stages to capture medical nuances. On the left, Stage 1 focuses on medical captioning, forcing the vision encoder to extract explicit features like lesion color. A frozen 72 billion parameter model scores these descriptions to provide feedback. Then, Stage 2 on the right shifts to diagnosis. Here, the model predicts diseases using those refined representations, receiving rewards based on its reasoning quality and classification accuracy. Well, Figure 2 details how the model achieves that virtual width using a method called frequency disjoint partitioning. On the left, it starts with a standard weight matrix in the spatial domain. The system applies a discrete Fourier transform to map these weights into the frequency domain, seen in the second panel, where components are split into distinct groups like the blue center and orange edges. Next, to create a specialized basis, it keeps only one frequency group, such as the blue parameters in the third panel, while masking the rest to 0. Finally, an inverse transform reconstructs this into the unique spatial basis on the right, which allows the model to specialize in different visual textures without simply adding more parameters. So, while Figure 2 explained the encoding method, Table 1 validates the reward signal used during training. It compares average caption rewards against diagnostic accuracy across a range of models to ensure they align. Notice the trend starting with the smaller QN 2.5 VL7B at the top, which scores about 6.2 on reward and 14% on accuracy. By the time we reach the massive QN3VL model at the bottom, the reward climbs to 7.2 and accuracy nearly doubles to 28%, confirming that the caption reward is a reliable proxy for medical reasoning. Okay, having validated the reward signal, Table 3 now performs an ablation study to pinpoint exactly where the performance gains come from. The bottom row shows the baseline model without the dynamic encoder or the first training stage, starting with a top 1 accuracy of just 15% on the Fitzpatrick 17K dataset. Moving up to the middle row, adding the Stage 1 captioning task triggers a massive jump to over 24%, proving that aligning text descriptions is crucial. Finally, the top row confirms that adding the dynamic visual encoding completes the package, pushing accuracy up to roughly 29%. So, scaling up to the main competitive analysis, Table 2 compares SkinFlow against industry giants on 2 major datasets. Look at the middle section for the Fitzpatrick 17K benchmark. The 7 billion parameter model, listed as Rs at the bottom, achieves a top 1 accuracy of roughly 29%. This effectively crushes the general-purpose baselines in the upper rows, where even the massive QN3VL 235B and GPT-5.2 stall around 17 to 18%. The right side shows the cell phone dataset, where SkinFlow dominates the top 6 accuracy with 79%, proving it is far better at keeping the correct diagnosis in view. Alright, to understand exactly why the accuracy jumped, Figure 5 visualizes the model's focus using attention heat maps. Take the knee lesion in the top row. The second and third columns show that baseline models like Quinn scatter their attention, producing faint, diffuse purple clouds over healthy skin. In stark contrast, the full SkinFlow model in the 5th column produces a bright yellow hotspot that locks directly onto the pathology. The histograms on the right quantify this behavior. While other models hesitate with low weights, the SkinFlow model, represented by the yellow bars, assigns high confidence scores to the specific lesion areas. Wrapping up, 2 takeaways stand out. First, raw parameter scaling is not the only path to medical precision. By optimizing information flow, this compact 7 billion parameter model outperforms massive generalist engines. Second, addressing diffuse attention is critical for reliable diagnosis. This points toward a future where specialized, efficient architectures dominate clinical AI. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.